This light feels bad. This light also feels bad. But this light feels pretty good. So what's the difference between all these bulbs? Why does the incandescent bulb, which is a technology from the 1800s, produce a better feeling light than the LED bulb and the fluorescent bulb, which are the modern day equivalents? A few years ago, I moved into a new apartment. Like most New York apartments, the lighting was pretty bad. It was too cold, too bright, and overall just left me feeling on edge. I wanted to make my lighting feel good, but I didn't really know where to start. I knew color temperature and I knew brightness, but fixing either of those never really seemed to fully fix how it felt. Even when I installed warm white LEDs and diffused them properly, the lighting still felt pretty bad. I wanted to understand what was happening from a physics and a biological perspective that made me really dislike my lighting, and what I could do to make modern lighting feel good. Before we can really start to address why modern lighting feels bad, we need to learn how to talk about lighting. We need to build up a bit of a vocabulary and an understanding of how you can measure light and how you can use those measurements to improve the quality of the light. The measurements of light can be grouped into three categories: spectral, which is the color content of the light; temporal, which is how the light changes over time; and spatial, which is how the light is distributed in space. All three of those measurements are critical to how a light source feels. If any one of the measurements feels bad, the light source is going to feel bad overall. In future videos, we're going to focus on the remaining aspects of light, but for this video, we're going to focus on the spectral qualities of light. All light is a mixture of colors. This was famously demonstrated by Sir Isaac Newton in 1666. Newton used a prism to spread out a beam of light into the individual colors contained within. When a beam of light hits a clear surface at an angle, the colors within the light each bend slightly different amounts. This process is known as refraction. A triangular prism is uniquely good at this effect, as the incoming light encounters two sides of the triangle, causing the separation of colors to happen twice and further spread out the beam. While this prism is helpful to show that white light is made up of colored light, it's not particularly easy to work with. Instead of using a prism, we can use a diffraction grating. Like a prism, a diffraction grating separates light into its component colors, but it does so through interference rather than refraction. As light passes through the diffraction grating, the light waves interfere with one another, causing different colors of light to emerge at different angles. Similar to a camera aperture, incoming light can be passed through a slit to improve the resolution of the color spread. Prior to adding the slit, you could see the rainbow smeared across the diffraction grating, but with the slit, you can see a sharp separation of the colors within the incandescent filament. Diffraction gratings are a helpful improvement over prisms as they are flat, making them easier to embed into measurement devices. Here's an example of an instrument with an embedded diffraction grating. This is a diffraction grating spectroscope. Light first passes through this slit, then through a diffraction grating before it exits through the eyepiece. If the spectroscope is attached to a USB webcam, an image can be captured showing the color composition of the light. With this tool, we can capture recordings of any light source and its component colors. This tool is also known as a spectrometer. Looking at the image captured while observing this incandescent bulb, you can see that there is more powerful light in the yellow and reds compared to the blues. The webcam-based spectrometer is going to be a great initial way to look at the mixture of color within any light, but it's not really accurate enough to conduct scientific research or further electronics development with. For that, we're going to need something like this, which is a scientific spectrometer that's purpose-built to collect accurate data about the mixture of color within a given light source. A scientific spectrometer combines a slit, a diffraction grating, and a high-precision image sensor. This sensor differs from the webcam sensor in that it captures all of the colors of light evenly instead of focusing on just RGB. Light enters through this fiber optic cable, passes through a slit, then through the diffraction grating before hitting the sensor. Light enters the fiber optic cable through the other end, which has a diffuser. If we take the same incandescent bulb that we observed with our webcam-based spectrometer, we now have enough precision to create an accurate graph showing the relative power for each color of light. Just like in the webcam image, you can see in the graph that the incandescent bulb has much more power in the yellows and reds than in the blues. Prior to the invention of fluorescent and LED lighting, basically all light that humans experienced was coming off of something hot. Fire, candle, oil lamp, incandescent light bulbs, and even the sun itself. Everything was a light source based upon heat. When something gets hot enough, it emits visible light. This is due to a process called blackbody emission. The defining characteristic of blackbody emission is that it produces smooth spectral power distributions. There are no sharp spikes and there are no holes carved out of the spectrum. At lower temperatures, around 1200 Kelvin, most of the visible light is red and orange. This produces a very warm white light. Think of a candle, the coals in a fire, or red-hot metal. If we observe a lighter with a spectrometer, we can see this in action. The curve produced is smooth, continuous, and contains mostly orange and red light. As the temperature of the emitter rises, the curve shifts from red to blue. At higher temperature, the spectrum shift results in a color composition containing increasing amounts of green and blue light, eventually producing the white light we associate with the sun. Measuring sunlight with our spectrometer shows a roughly blackbody spectral power distribution. Note that there are a lot of artifacts introduced in the spectrum by selective absorption as sunlight passes through the Earth's atmosphere. In 1900, Max Planck derived a formula that was able to predict the spectral power distribution of a blackbody radiator based on temperature alone. This formula is what was used to generate the previously shown graphs and is where the Kelvin numbers printed on light bulbs come from. A 2700 K light bulb, which is roughly temperature of an incandescent light bulb, is emulating a blackbody emitter at 2700 degrees Kelvin. The reason to care about blackbody emission is not because old lighting technologies are inherently better. If you zoom out, an incandescent light bulb wastes a tremendous amount of energy generating light that's not visible to humans. If you want to emit light in an energy efficient way, heating something up and then relying on blackbody emission is not the way to do it. But from a spectral standpoint, blackbody emission is really beautiful. It's a smooth, continuous spectral power distribution, and more importantly, it's the spectral power distributions that our eyes and our bodies have evolved with for hundreds of millions of years. The human visual system evolved to expect blackbody emission. So now we have two things. With the spectral power distribution, we have the ability to look inside the light to see the mixture of all the colors. And with the blackbody emission, we know the mixture that our brain is looking for. With those two things, let's go back and look at the bulbs again. First, let's start with the fluorescent bulb. A fluorescent bulb generates light by electrically exciting mercury vapor. The excited vapor emits mostly ultraviolet light, and phosphor coatings on the glass convert that ultraviolet light into visible light. It is efficient, but as you can see here, the spectrum looks nothing like a blackbody emitter. The spectrum is spiky because it's built from atomic emission lines and phosphor conversions rather than heat. Now let's look at the LED bulb. Inside the bulb, the actual LED is blue. Some of that blue light is directly emitted, but most of it is converted via a phosphor coating. The phosphor absorbs blue light and re-emits it at longer wavelengths: green, yellow, orange, and red. There are a couple issues with this process. First, the phosphor needs to absorb the blue light before it can convert that energy into other colors. This means it cannot efficiently emit light right next to the blue pump wavelengths. This often leaves a weak region in the cyan part of the spectrum between blue and green. Second, the phosphor does not produce a smooth spectrum in the converted light. While the light coming out of the LED bulb may look warm white to your eye, the spikes in the spectrum are going to result in unnatural illumination of the environment. Anything in the environment that has a color corresponding to one of these spikes is going to appear overly saturated. As we measure this LED bulb, note the deficiencies we just talked about. There is a big gap in the cyan region, and in the yellow-red region there's a lot of spikes due to the phosphor. This will produce a warm white, as there is more red and yellow light than blue light, but it's not going to produce light that matches blackbody emission. Now let's return to the footage from the beginning of this video. Let's ignore what the bulbs look like, and instead let's focus on how the bulbs illuminate the table. If you look at the incandescent bulb, you'll see that the table is illuminated in a very natural way. The coloring of the table looks smooth and warm. It's the exact kind of lighting your brain expects from a blackbody emitter. Moving on to the LED light, things start to look a little less natural. While the LED's color temperature is a bit cooler, the overemphasis of light in the amber and the lack of deep reds leaves the table feeling flat. Finally, let's look at the fluorescent. The fluorescent bulb produces lighting that quite frankly looks nauseating. The green and amber spikes in the spectral power distribution are causing those colors to be significantly overrepresented in the wood, and the lack of red light prevents any warmth from being experienced. While the example of a table is simple, you can see here how the spectral power distribution of your lighting can significantly change how you experience your environment. So how do we fix this? How do we make a modern bulb that feels like a blackbody emitter? What we want is something that produces the spectral power distribution of a blackbody emitter in the visible range, while wasting no energy producing light outside of the visible range. Further, it would be great to have a bulb that has precise dynamic control over each color within the visible range. If we can control the power at each color, we can precisely emulate a blackbody emitter, whether it be the midday sun at 6500 Kelvin or a candle at 1200 Kelvin. While it would be incredible to have this precise of control, it's not technically feasible with existing technology. LEDs produce spectral power distributions with some width to them. They cannot make narrow lines. We can, however, combine a set of colored LEDs that are spread across the visible range to give us a coarse but sufficient ability to shape the spectral power distribution within the visible range. A light that is designed to shape the underlying spectrum instead of producing a singular color is called a spectrally tunable light.
Now this video has come full circle. A few years ago, I set out to learn why I didn't like the lighting in my apartment and what I could do to make the lighting feel good. I didn't like the lighting in my apartment because all of the bulbs were outputting unnatural spectra, and what I could do to make it feel good would be to replace them with spectrally tunable lighting. Spectrally tunable lighting has the promise of feeling good as it can accurately recreate the blackbody emission at any temperature. Additionally, spectrally tunable lighting enables this whole new design space in which the underlying spectrum is tailored to the environment that the bulb is in. My issue was nobody was making this product. Spectrally tunable lighting did exist, but it was limited to lab and research environments. To improve lighting, we need spectrally tunable lighting not just in lab and research environments, we need it everywhere. To achieve this goal, I started a new company, Enody. Enody is a contraction of enhanced and blackbody, and that really encapsulates what I'm trying to do. The goal of Enody is to develop the future of lighting. That starts with accurate recreation of blackbody emission and then enhancing the light from there. To do this, Enody is starting by making spectrally tunable lighting available to everyone with our first product, EPO1. EPO1 is a spectrally tunable light. It has no white LEDs. Instead, it contains 32 colored LEDs spread across the visible spectrum. EPO1 was designed from the ground up to be a development kit to push lighting forward. You don't have to work in a research or a lab environment anymore to access spectrally tunable lighting. It has an SDK available in multiple programming languages, and with a touch-sensitive base, it functions as a great nightstand or a desk lamp. Now, let's look at how EPO1 compares to traditional LED lighting.
Instead of blue pump-based white LEDs, EPO1 features only colored LEDs spread across the visible spectrum. When these LEDs are accurately mixed together, they create spectral power distributions that match blackbody emitters more precisely than existing LED lighting. This can be seen when looking at the spectrum of EPO1 while it emulates a 2700K blackbody emitter. The spectrum is smooth with a much smaller cyan dip and no sharp spikes throughout the whole spectrum. If we overlay the ideal blackbody distribution, we can see that EPO1 is a close match throughout the entire visible spectrum. If we compare EPO1 to an existing LED bulb, you can see the spectral power distribution matches the ideal blackbody emitter much better. Additionally, EPO1 extends further into the reds, allowing that true warm feeling light. This improvement in precision is not just in warm lighting. When observing EPO1 and a standard LED bulb fade from 5000K to 1000K, you can see that EPO1 has a more accurate spectral power distribution across the entire blackbody range.
You may have noticed that EPO1 still has peaks and valleys when compared to an ideal blackbody emitter. There are inherent limitations to all LEDs that prevent us from perfectly recreating the spectrum. But what EP01 does offer is a new way of thinking about lighting. Instead of accepting the fixed spectrum of any light bulb, the spectrum has now become something that we can measure and tailor to the underlying environment. Now I want to take a minute to talk about how EP01 was made. I personally designed every element of EP01, from the physical enclosure to the electrical design to the firmware and the host site SDKs. All of it was done in-house by me. I truly believe that spectrally tunable lighting is the future of lighting, and to get there, we need a fully integrated product accessible to everyone. The design process was long, with a lot of prototypes, but I'm happy to say that EP01 is now shipping with all units assembled in Enody's Brooklyn Navy Yard workspace. Building a spectrally tunable light is a lot different than building traditional LED lighting. You cannot just combine LEDs that are pre-measured to a certain color temperature and mix them with a common mix. Every LED is slightly different. Two LEDs with the same exact part number can have different peak brightness, different peak wavelength, and different performance at various power levels. If a spectrally tunable light is to accurately mix LEDs together, it needs to know the actual behavior of every LED within. During production, all Enody devices are individually calibrated. The device turns on each LED in controlled configurations and measures the output with a spectrometer. With this data, we can build up a coherent model of how the lamp behaves. This part of the assembly process is what makes spectrally tunable lighting work. Without this data, the software of the lamp is just guessing at the spectral output of the lamp. But with this data, the lamp has concrete knowledge of its own spectral power distribution. So we have all this data, but how do we generate the underlying mixes? The answer is in optimization. The same frameworks that are used to train modern AI models can be repurposed to determine the mix of LEDs in spectrally tunable lighting. More on that in a future video. So EP01 is a physical product, but it's also a manifestation of Enody's calibration and optimization infrastructure. The lamp is produced, the LEDs are measured, and optimization turns that into a usable spectrally tunable lighting system. This is where I think lighting now gets incredibly interesting. We're no longer working with fixed spectrum light bulbs. We're now working with a software-defined spectral source. You can output the light that's good for humans just as easily as you can output the light that's good for spinach. The spectrum can be shaped perfectly for the environment you're in. This is also why Enody owns our assembly line. With an in-house electronics assembly line, we can rapidly iterate both on product and on the LED configurations within a product. Additionally, we can produce custom LED configurations for our customers very rapidly. Want a lamp that has no blue light? Perfect. We just won't put blue LEDs on the board. If you're interested in custom LED configurations, hit me up. We can make cool stuff together. I want to end this video with a quick explanation on where I envision Enody going. I don't think the average person needs to, nor quite frankly should, care about spectral power distributions, blackbody emission, and the intricacies of a manufacturing process. What I do think is that the modern lighting industry has condensed lighting down to a few metrics that are not accurately depicting how lighting works. They've given us brightness, color temperature, and a few quality metrics, but that's not depicting the whole story. Light is so much more important and rich than that. Light is the driving force in evolution. Light produces all of our crops. Light lets us see. Light tells our bodies when to wake up and when to go to sleep. Light needs to be taken seriously as the biological influence that it is. Our light shouldn't just look beautiful, it should positively affect our health. We should know exactly how we're spending energy on lighting and exactly how it's affecting our bodies. In the future, your bathroom should improve your skin, your office should help you focus, your doctor's office should help you relax, and your bedroom should help you go to sleep. All of these things can be accomplished with proper lighting. The first step is measurement. If we can measure why we feel bad, we can begin to fix it. In this video, we covered the spectral aspects of light, how to measure it, what feels natural, and why two bulbs at the same color temperature can leave the room feeling dramatically different. But there is still so much more to lighting. There's temporal, there's calibration, optimization, biology, and so many more topics to cover. But I want to leave you with this, and this is the core point. Modern lighting should not force us to adopt to whatever was easiest to manufacture. Modern lighting needs to adapt to the environment it's illuminating and the life that calls that environment home. Thank you for watching. Until next time.